In this video, we're going to develop the equation for the conservation of linear momentum. So the starting point for this is the same as for all of our conservation equations. We're going to start with Reynolds Transport Theorem. Now, just like we did for conservation of mass, we need to identify three quantities in order to substitute into the general form of Reynolds Transport Theorem. So the very first thing we do is say we're looking at conservation of linear momentum, so we let B equal linear momentum. And remember, linear momentum is mass times velocity. Now here we see the first big difference between conservation of linear momentum and conservation of mass. Momentum is a vector quantity. Mass was a scalar, so we didn't see any vectors in that equation. But momentum is a vector quantity. It has direction. So that means the conservation of linear momentum equation, every term is going to be a vector. So we see that coming in right away because B is going to be set equal to mass times velocity, where velocity is a vector. So the second thing we need to do is identify what is beta for linear momentum. Well, beta is the amount of B per unit mass, so beta is just the velocity, and again, a vector quantity. So momentum per unit mass is velocity of the fluid. The last thing we need to do to prepare to use Reynolds Transport Theorem is identify what is the conservation law that we're going to substitute into the left-hand side of this. Well, the rate of change of the momentum of a control mass, so the left-hand side of this equation, is equal to the sum of the forces on that control mass. And that's Newton's second law. The rate of change of momentum of any identified mass, a chunk of stuff, is equal to the sum of the forces acting on it. And again, remember, both sides of this equation are vectors. Momentum on the left, forces on the right. So when we're accounting for all of these forces acting on our control volumes, we need to pay careful attention to what direction those forces are acting. So these are the three things we need to identify to prepare Reynolds Transport Theorem for conservation of linear momentum. So here are those three things substituted into our general form of the equation. The sum of forces is on the left-hand side, and we're going to be talking quite a bit in this video about what that looks like. What are all of the ways that forces can be exerted on our control volumes? On the right-hand side, we've just substituted velocity in for beta in the two spots where beta occurs on the right-hand side of the general Reynolds Transport Theorem. So those V's are substituted in for linear momentum. Now realize that those V's are not relative velocities. Now remember back when we developed Reynolds Transport Theorem, we talked about this V sub r term. This V sub r denotes the velocity of the fluid relative to the control surface. So if our control surface is moving for some reason, we need to make sure in that term that we're using the velocity relative to the control surface. And that subscript r is there to remind us to do that. But realize these other two V's that have appeared when we substituted in our beta value do not have an r on them. So these are not velocities relative to the control surface. These are absolute velocities, and by that I mean they're velocities relative to some inertial coordinate system. So not a coordinate system that is accelerating, but a coordinate system that is either stationary or moving in a straight line at a constant speed. So an inertial coordinate system. Those two V's are relative to the coordinate system, not to the control volume. And we'll be talking quite a bit about that as we apply this equation to different problems. So the uniform version of this equation does the same thing as the uniform version of conservation of mass. It replaces that surface integral on the right-hand side by two discrete sums, one over the discharges, one over the inlets, and each of them is mass flow rate times the velocity at those respective discharges and inlets. So the same simplification here due to the uniform flow assumption. Now, if we also assume steady state, remember this is the unsteady term. This is the only spot where a derivative with respect to time appears. So if we also assume steady state, then this term is gone. So if we have both steady state and uniform, then it says that the sum of the forces on the control volume is equal to the sum of mass flow rate times velocity at discharges minus the sum of mass flow rate times velocity at the inlets. So these are all of the forces on the control volume. This is the momentum entering the control volume, and that's the momentum leaving the control volume. So if we tie this back to the illustration that I gave right at the very beginning of the control volume analysis section of the course, we were looking at air flowing over top of an airfoil. And we talked about the fact that the momentum entering that control volume was different than the momentum leaving. So now we're taking a look at the equation that would allow us to figure out those forces. So the force on that airfoil would be part of this left-hand side, and those different velocity profiles at the inlet and discharge would give us different momentum entering and leaving our control volume. Now, the last thing we need to do here in order to come up with our working equation for linear momentum problems is we need to take a look at this term in quite a bit more detail, because there are several ways that forces can be exerted on control volumes, and we need to take a look at all of the ways that that can happen, essentially to finish off the left-hand side of this equation. So next, we're going to look at all of the forces on the control volume. So the first thing we do is something that we did also in the hydrostatics section of the course. We break those forces up into body forces and surface forces. Now there we were just looking at a very small differential element in the fluid. Here we're looking at large control volumes that surround entire components or systems, but the principle is the same. All of the forces acting on our control volume can be broken down into body forces and surface forces. Now further, we can break these surface forces down based on their direction. We can exert a force normal to the surface, or we can exert a force tangential to the surface. So we're going to take all of our surface forces, break them down into normal and tangential forces. So let's take a look at a possible control volume here. And again, the shape of the control volume is arbitrary at this point. So first of all, remember that body forces are forces that act on the material inside of the control volume. And that accounts for all of the material inside the control volume. So the very first contribution to our sum of forces is going to be this body force. And that's the weight of everything inside of the control volume. The surface forces can be normal, so in other words perpendicular to the surface, or they can be tangential, parallel to the surface. So now we want to quantify these things. Well, like I say, the body force can actually be due to gravity or magnetic fields. We're not going to look at any situations where magnetic fields are important in this course. But body force due to gravity is likely to be important in quite a few problems. So we can quantify our body force as the integral over the volume, and remember this V is our entire control volume, of rho times G times dV. So this is the weight of everything inside the control volume. Remember, it has to be a vector quantity, and it's the direction of G that gives it its direction. So we have to certainly set up a coordinate system, and we need to know what direction is G relative to our coordinate system. So the body force is the weight of everything in the control volume. So notice it's not just the fluids in the control volume, it's everything. So if our body force enclosed an entire airplane wing, or perhaps the entire airplane, the solid objects in there, the aluminum and plastic and whatever the airplane is made up of, would also be part of that weight. Everything inside the control volume. Now, in terms of normal forces on the surface of the control volume, those are due to pressure forces. So, although our control volume is a hypothetical surface, if we're going to calculate the force of everything outside of our control volume on our control volume, which is what we're doing here, the pressure on that surface needs to be taken into account. So we're calculating here a force on a surface due to a pressure. Well, from our work in the statics section of the course, we have an equation to do that. So that's going to be the integral over the surface, only this is now our control surface we're talking about, not some physical surface like the hatch of a submarine or something. It's our control surface. But everything inside of here is exactly the same as when we were doing hydrostatics. So we have pressure, so that's the pressure at different places on the control surface. Our unit normal still defined the same way, perpendicular to the surface, projecting out into the surroundings, and then dA is an element of area on that surface. And this still has a negative sign out front because the pressure force is always in the opposite direction to this unit normal. So we're familiar with how to set up this term from doing our hydrostatics section of the course, so a lot of those things will apply here as well. So exactly the same equation. Now the difference, of course, is that information about this pressure is not going to come from the basic hydrostatic equation. It has to come from somewhere else, because now we're looking at fluid dynamics. The situations we're going to apply this equation to, the fluid is certainly moving. So that pressure information can't come from the basic hydrostatic equation anymore, but we'll talk where it comes from when we do examples. So we have our body force, weight of everything in the control volume, and we have our pressure force, the normal forces on the surface of the control volume. Continuing on with surface forces, we also have the possibility of there being tangential forces, or forces parallel to our control surface. So those are due to viscosity in the fluid. So in our final form of the equation, that's just going to be represented by this viscous force term. So these are shear forces due to viscosity. Now the last member of the left-hand side of our equation, the sum of all of forces, is called a reaction force. So a reaction force happens when our control surface cuts through a solid object of some kind, as it often does. Not in every problem, but in quite a few of the problems we're going to look at. When we identify our control surface, we need to realize it's actually cutting through some kind of a solid object. So the reaction force is the force in that solid object that we need to take into account in our sum of forces. So it's the force that the object exerts on the control volume. So let me just try to draw a little illustration here. Again, let's say that we were looking at our airfoil here and flow from left to right here, and we wanted to calculate the forces on this using control volume analysis. Well, we would draw our control volume around this. We would look at all of the momentum coming in and the momentum leaving. But when we set up our linear momentum equation, we need to realize that if we were doing a wind tunnel test of this thing, let's say, that airfoil is not just going to sit in there without being supported. It needs to be attached to something in order to stay in that position. So in a wind tunnel, there'd be some kind of an attachment between this airfoil and the surroundings. So I'm going to show that here just as a strut of some kind bolted to the ground. Okay, so this has to exist in order for that airfoil to stay in that position as the air enters our control volume, interacts with that object, and then leaves. Well, when we're doing a control volume analysis, we need to account for all of the forces on this control volume. So we talked about pressure forces pushing on this control surface. We talked about shear forces perhaps acting on this control surface. Well, we need to account for the entire control surface. And right down here, there's a very important part of the control surface. Notice that our control surface here cuts through a solid object. The airfoil itself is completely surrounded by our control volume, but right here we're cutting through a solid object. Well, this portion of the strut out here is exerting a force on this portion of the strut in there. So at that part of our control surface, there is a force acting on our control volume. And that is called the reaction force. And really what it is it's a very, very small portion of our control surface. So our pressure force and our viscous force terms cover off anything that might be happening where the control surface is in contact with fluid. But this special term here, this reaction force, is accounting for this small portion of our control surface where the surroundings, this thing down here, are exerting a force on our control volume. So that's the reaction force. And notice that that's very important in this problem because that reaction force is the drag force on this object. In fact, even if there was a lift force, it would show up here. So when we apply the conservation of linear momentum equation to this situation, it's actually the reaction force that we're interested in. That will be the forces generated by this airfoil section, both in the lift and the drag directions. So reaction force is an important member of this sum of forces. So now we're ready to bring all of these things back into the general form of the equation. So this is our general form of Reynolds Transport Theorem for linear momentum. And the left-hand side of our equation here is all of the forces that act on our control volume. So we have our body forces, our normal forces due to pressure, our tangential forces due to viscosity, and this reaction force due to any solid member that might be cut by our control surface. So that's the left-hand side of our equation, and all of those forces give rise to some change in momentum. So we add these all up, and they need to be balanced by the change in momentum. So the right-hand side of this equation is the change in momentum that results from all of these forces. Well, there's two general things that can happen that change the momentum of the system. Either the material inside the system is speeding up or slowing down or maybe changing direction, so its momentum is changing with time. So when we look at our system now, and when we look at it 2 or 3 seconds from now, the total momentum in the control volume is different. So that means that there's a change with time. So this is called the unsteady term. And if the momentum of the stuff inside of our control volume is changing with time, we need to keep that term and handle it properly. And we'll be seeing some examples where that's the case. Now the other possibility is that the material entering and leaving our control volume has a different momentum. That's a more common situation, and in our early examples we're going to be seeing that happen a lot. So if the material entering and leaving has a different momentum, then there must have been a force in order to cause that to happen. So this term is concerned with material entering and leaving our control volume, and we can tell that because it's an integral over the surface. It's concerned with what's happening on the surface. This doesn't care what's happening inside the control volume. It only cares what's happening on the surface. So in a series of examples now, we're going to be applying the linear momentum equation that we're looking at now to a number of scenarios and learning how to handle each of these terms, which ones are important in which scenarios. So we'll see you in those examples.